I have here, I have thermometers, and I'm measuring the temperature of this airspace and the water. And notice the two thermometers, they're about the same right now. Let's start at the hot plate. Now, I want you to make a prediction. We're talking about in phase change that when I boil the water, the steam and the boiling water should stay at the same temperature until one or the other is gone. So I want you to make a prediction. What do you think is going to happen when I get this to boiling, the liquid to boiling? What is going to happen to the steam above it? The steam above it. All right, make a prediction. That would mean write it down.
I think we should go into the classroom.
It's cold outside.
I think that's cold outside.
It's colder in Mr. Brumbach's office.
I think it's warm.
Okay, you're welcome to go.
What do you do? It's warm or I'm going to set out water going in?
What?
What do you do?
Subtle warming. Maybe not unsettled. Maybe a very unsettled. As we go, but I want to go back to this a little bit. We did this last time, this diagram. It's in your notes already. And just, I think we talked about a little bit just to reiterate that point. That water, remember, one of the unique properties of water is that if I take the solid, I put it under pressure, it will become a liquid. But conversely, when I put pressure on the liquid, it will never become a solid. Unlike other materials, if you put pressure on the liquid, it will become a solid. Remember, we passed around the little propane tank, and we've said that. But this is one of those unique properties of water that keep the earth from freezing up. Because think about it, on the bottom of the oceans, high or low pressure? High, very high pressure. But every time you go down underwater 10 meters, about 30 feet, you go up 1 atmosphere of pressure. Now, we live at 1 atmosphere, so you go down 30 feet of water, you're going to be at 2 atmospheres. Go down another 30 feet, 3 atmospheres, 4 atmospheres. And you can see, you get down to the bottom of some of these deep areas, I mean, we're talking over 5 miles deep. Think about what the pressure is like at those depths. So if water froze when it got under pressure, which was what everything else does, what would happen to basically the oceans and the deep water lakes? They would all do what? Freeze. At least to a certain depth, they'd all be frozen, regardless of temperature. And the temperature at the bottom of the ocean is about 0 degrees. It's about 1 to 0 degrees at the bottom of the ocean. But it's under a lot of pressure, so it takes a lot more to do that. It takes a higher temperature to actually freeze it, things like that. Actually, yeah, higher temperature. Lower temperature, but it's still down there. It's not frozen on the bottom. So, on our diagram, this is one of those unique properties. But again, like water floats. The ice floats. It doesn't turn to ice. Unique property of water. It's the only thing it does that. Really, okay? Okay. All right. So just quickly, we're starting into thermodynamics. Now, this is the idea all temperatures now have to be in kelvins. So you need to go look back. How do I make Celsius to Kelvin? So a lot of questions will refer to Kelvin temperature. When they're talking about doubling energies, you would double the Kelvin temperature. You know, if you want double the Kelvin temperature, that would be doubled energies, things like that. So temperatures here are Kelvin. This diagram in your book kind of gives you an idea in the grand scheme of things. Remember, water melts at 273 and boils at 373. So this is kind of where we live in this area here. But down here, you have where hydrogen boils, oxygen boils, all this stuff. You work your way up, all the way up to hydrogen bombs and things like that. Grand continuum, what kind of temperatures we're looking at in the Kelvin scale.
Does it draw all that?
No, it's in your book. I would make a note where to find that diagram in the book. Now, what we're going to talk about today is basically the first law of thermodynamics. Now, the first law of thermodynamics is basically a restatement of the law of conservation of energy. That's what the first law of thermodynamics is. but you're not. Whenever heat is added to a system, it transforms to an equal amount of some other form of energy. Basically what it says is you can break even. The best you can do is break even. I put in heat, I'm going to get out the same amount. That's the best I can do. I can never get ahead. I can never get more energy out than I put in. And remember, thermodynamics has to do with that transformation of heat into mechanical energy. It's really what we're studying here. When you study thermodynamics, it has a lot to do with engines, different types of propulsion plants, power generation, things like that. Because like the steam plant, well, a steam plant, if I hook it to a propeller, I make my ship go forward. If I take that steam plant and I hook it onto a wheel, I have a train locomotive. I can put on a wheel, I have a car. Steam-powered cars were the muscle cars of their day. Stanley steamers. You could do about 60 miles per hour in a Stanley steamer at a time when most cars, at best, gasoline-powered cars maybe went 30 miles per hour. So these steam-powered cars were the muscle cars of their day. The only trouble, you can only drive about 20 miles or so before you had to fill it back up with water. That's one thing with steam engines, that periodically you have to stop and you got to put water in the tenders for the steam. You got to carry it with you. If you've ever looked at if you ever gone to the train museum in Sacramento, they have the old cab forwards that used to bring trains basically over the Sierras, and there's like a 20-mile, I think it's a 20-mile stretch in the Sierras that the engine would use something like over 20,000 gallons of water to go it's 8 miles, I think. To go 8 miles, it used 20,000 gallons of water because it's so steep in the Sierras on that. Southern Pacific used to have some very specialized locomotives, even diesel era, to get over the Sierras. That's one of the hardest railroad areas around. And so this all relates to internal energy. And how do we see internal energy? If I change internal energy, what changes that I can measure? An object's what? When internal energy goes up, what goes up? T word. Temperature, internal energy. So we're looking at change in temperature of a substance at work. And basically what it comes down to is a change. Wow. A change in internal energy is equal to the heat added or removed plus work done on or by the system. Now, heat added or removed, that's pretty easy. We've been talking about, yes, sir. Change in internal energy. Energy.